All right, everybody. What kind of Halloween fun did everyone have last night? None? Zero? Really? You had fun? Yeah, okay. You're doing homework, right?
I did do homework this morning.
Oh, okay. But you didn't do it last night. Oh,
I did this morning before your class. And then I started next week.
okay. Well, congratulations. Thank you for telling everybody. They're all very happy for you. Let's see. So, yeah, I got the idea like this morning, my 8 o'clock class. Boy, it was empty. I just, so I assume that people, at least in some classes, must have been out late last night. But maybe for some of you, it's like it's a 3:30 class, so you can wake up by this time. So, no. If you partied, you're just not going to admit it, are you? Yeah. Okay. This is just let's just have a one-on-one conversation today. It kind of seems like where this is going. So, today being November 1st, first of all, welcome to November. That's kind of fantastic.
Welcome to Christmas.
Basically, yeah. So we survived, like a week of August, and then September and October. We're basically done, right? It kind of feels like it.
2 more months.
It's not really even 2 more months. We've got like 2 weeks and then 3 weeks, I think. So it's like a month-ish, which is basically nothing, right? Yeah, it's like we're done, so let's just leave. Let's see. So what I wanted to say is it's November 1st, which is kind of a holiday in a way because it's the day that all the Halloween candy goes on sale, like everywhere, right? So the question is, which day to go? The day after? Do you wait 2 days, 3 days, 4 days? So you keep in mind, like today it's like half off, right? And then if they don't get rid of it, then it's like 60% off. And it's like 70% off.
But then you left
Yeah. See, we need a graph, right? Because there's candy availability that starts high, and then it's going to fall off in the coming days, probably like exponentially. It's going to rapidly drop. But then, like we got this other curve where the like discounts are rising.
Okay, but how do we rate candy?
Which candy do you like?
Exactly.
We can just assume all the good stuff's going to go first.
Yeah.
So,
That's what I was like, we can't buy it.
Right. Even so, those two curves have to cross somewhere. I don't know if they cross like today, or if it means you're supposed to wait a couple days and get the best deals on the remaining good candy.
Well, we can't afford 50% off candy. Maybe you should not spend money on candy. Who knows?
Well, that's a good point. But the thing is, if you can get 50% off candy instead for 80% off, I can wait a couple days. So here's what we need to do. As a class project, every day for the coming days, we need just a few people to like drop in a couple of stores and make a note of how many days it's been since Halloween and what the current discount level is. And then if we all pull our data between like now and next Tuesday, we can plot a very nice graph and we can actually figure out which is the optimum day to go buy our candy. And then we'll be ready for the next holiday.
It'll be too late.
Well, it'll be too late for this one. But, I'm willing to sacrifice one Halloween for all future Halloweens.
Yeah. We'll post our research and we'll get another one prize.
Exactly. Because this is really worth something. It's much like, you should always buy a large pizza.
Oh, extra large.
But the biggest pizza that's offered is what you should always buy. None of this medium crap, all right? Because why? Area of a circle, pi r squared. R squared. So you're like 16 inches, 18 inches. Who cares? First of all, those were both big pizzas. But that extra 2 inches doesn't sound like a lot, but then it's squared, right? So they may charge just a little bit more for a lot more surface area. So things we've learned today so far, always buy the biggest pie. Yeah, so it applies to other kinds of pies besides pizza pies, of course. Like biggest pie is best for your money. And we need to do some research in the coming days. So if you take any data at all, email me. If you find yourself in CVS or Walgreens or wherever candy is sold, let me know. I need to know discount levels. Sound good? Yeah, we're going to publish this. It will be fantastic. I might put your names on the paper.
Okay.
Like we'll have a big author list like this big. It'll be fantastic. So we need to do this problem. Yeah. So what we're going to do is work this problem. Then I'm going to teach you a new technique, and then I'm going to give you another problem. Maybe with some other stuff kind of thrown in the middle there. Okay? Let's see. So stepping through this thing, I already told you that you could redraw the circuit like this, which is a little more clear, less confusing, but you might wonder how in the world we got from there to there. Okay? So let's think a little bit about what's happening in this circuit, starting at the positive side of the battery. Let's imagine the charge leaves this point. Okay? So from that point, notice nothing really happens until we get here where there's a three-way fork. Okay? I can go along this right path that includes this resistor, which in this one is 12, and go around to the 5. I have the option of going straight down, which just goes through the 5, or the option of going straight left, which goes through the 10. So over here on this diagram, I went from the positive side of the battery to a place where I can go down one of those 3 branches. Good so far? Yes, maybe. Trace all of them around, and you'll see that they first re-meet each other at this point. Okay? So all 3 of those, the 10, the 5, and these 2, all come back around to that point. So I just immediately recombined them. Okay? Are we still okay with that? Is everybody happy? Maybe a little bit? So once we get to this point where they've recombined from the bottom, the left, and the right, the next thing to do is go to the 10 ohm resistor and then back to the battery. So after they recombined, the next thing in the path is the 10 ohm resistor and back to the battery. All right? So a few things are sort of nested here. The 12 and the 5 are in series, but that combination is in parallel with both the 10 and the 5. All of that combined together is in series with this one remaining resistor. So you've got a series inside a parallel, which is inside of a series. Ooh, fancy, okay? So let's step through that, first of all, finding the equivalent resistance. So if it's okay with you, I'm going to number these resistors so we can kind of work it the way we did with that other example. So let's see, let's call this one resistor 1, and 2, and 3, and this one will be 4, and this one will be 5. So over in my other diagram, let's see, this is resistor 1, resistor, ooh, that's 3, this one's 2, that one's 4, and that one's 5. Otherwise, it just gets a little bit confusing. Like I'm talking about the 10 ohm resistor. Which 10 ohm resistor? You know, everything's just kind of lost at that point, okay? So we're going to start by combining R4 and R5. R4 and R5 are in series, which means that the current through them is going to be the same. Whether we're talking about one of them individually or the combination of them. All of that has the exact same current through it. And I can find the equivalent resistance for 4 and 5 by just adding 4 and 5. So let's see, it looks like R4 is 12, R5 is 5, so that's just 17 ohms. Good so far? Series resistors are the best, yes? Yeah, fantastic. Okay, so let's redraw the circuit now, and very quickly, we need circuit drawing music. What would that even sound like? I fully expected someone to just blurt out circuit drawing music right then. It would hum something. I don't know what it would be. So it looks like this now, right? I've got the 3 in parallel, and then the 1 off by itself. So this is resistor 3, or excuse me, resistor 2, resistor 3, and the combination 4, 5. So we're going to combine all of those. So we can say that resistor 2 and resistor 3 and resistor 4, 5 are in parallel. So then we'll have 2, 3, 4, 5 all put together. So 1 over R2, 3, 4, 5 is 1 over R2 plus 1 over R3 plus 1 over R45. And we have all of those numbers, but I don't have this intermediate value, so somebody, could you calculate R2345 and please tell me the right answer? Because if you don't, all is lost and the whole class will hate you. No pressure or anything. 2.61, and you did take the reciprocal at the end. Yes, the last reciprocal. Yes, okay, good. Just asking because that's a common mistake. Okay, so resistor 2345, which you can't really see there, is 2.61 ohms. One thing I didn't put in there is when they're in parallel, what do they have in common? Voltage or potential when they're in parallel. So if I could squeeze that in here somewhere, let's say that V2 is equal to V3 is equal to V45 is equal to V2345. Okay, they all share the same potential or the same voltage. So let's redraw the circuit again and see where that gets us. And to do that, I need a new slide. We are just out of space. Let's make that a little bigger. And let's see, what do we have now? We've got this resistor, and then the battery, and then we've got this. And this is just R1, and this is R2345. Clearly, they are in series. So R1 and R2345 are in series, which means they have the same current passing through them. And that current is the total current. It's the only current. There are no other paths. All the current that leaves the battery passes through both of those resistors, okay? So let's see, Req, which is the total, is R1 plus R2345. And let's see, what is the value of R1? It's 10. And our last resistor was what, 2.16? I think.
It's actually 2.79.
2.79. Are you sure?
Yes.
Yes. Okay, I'm gonna go back over here. 2.79. I even flipped the digits there anyway. 2.79. Thank you. So let's see. Over here we have 2.79. So that's 12.79 ohms. That is the total equivalent resistance in the circuit, right? Once I have that, I'm able to find the total current using Ohm's law. So I can say that V total is equal to I total times Req, and we can rearrange that and say that V total over Req is the current. What was the given voltage? How much? 5? 25? 67? 9? How much? 25? Okay, thank you. So 25 over 12.79 is 1.96?
Yeah.
Okay. That's 1.96 amps. That is the total amount that's leaving this. This is 1.96 amps. Okay? So we have been asked a couple of things. Going back to this, notice we want the current through the 12 ohm resistor. The 12 ohm resistor is what we call resistor 4. Okay, so we want the current through resistor 4. So we're going to have to sort of step our way back into that big combination of 2, 3, 4, 5 until we can isolate just the current through resistor 4. So I'm going to start by saying V2, 3, 4, 5 is equal to I2, 3, 4, 5 plus R2, 3, 4, 5. We know that current and we know that equivalent resistance. So I can find the potential across that combination. So let's see, this is 1.96 and this is somewhere, 2.79, which gives me what? I have the final answer, but none of these intermediate answers. What's that? 5.45. Okay. So 5.45 is the potential difference between just before this big combination and after. Okay, that's the potential difference across that. So if I go back and look at my overall diagram, that is the potential difference between here and there. Notice all those things are in parallel. They all share that same potential difference. Agreed? Between the two red dots. And we actually made a note of that somewhere, right down here. Notice, V2345 is equal to V45, V3, and V2, all the exact same. We are concerned about V45, right? Because we're looking for resistor 4. So let's go back over here. And we know that this is equal to V45. Using our little notes to ourselves. You don't have to do all that if you feel like you've kind of got it in your head and you understand what's happening. I like to keep records of it because I get lost in the circuit. It's easy to find yourself buried in the middle of the circuit. No idea how you got there and no idea how to get back out. So keeping a lot of notes along the way is quite helpful. So let's say that V45 is equal to I45 times R45. We can use this below, and we know what this value is, so I can solve for I45, which is V45 over R45. So this is going to be 5.45 over 17, I think. 0.32. Okay. And if you go back and look at the notes that we have on the previous slide, this is also equal to I4, which is what we were looking for. What we were looking for. Yeah, I know, it's hilarious. That's the current through that one resistor. So it's basically the process of taking the circuit, putting everything together, your eyes, combining it all you can, and then sort of picking back apart the thing that you want to know something about, kind of digging into the combinations once again, using Ohm's law repeatedly. Okay? Question?
Is I2345 the same as I total?
Is I2345 the same as I total? Yes. So the current that passes through this is the same as the current that passes through that, and the same as the current that passes through the battery. All of that is the same. We can see that right here. Anyone else? You feel pretty good? You can do this? Do you think something like this could be on an upcoming exam? Boy, it sure feels like it, you know, just something about it. Feels right. Feels like something someone would put on an exam. I don't know who would do that. No idea. Because I don't write the exams. They just come delivered from the heavens. And then I print them. Yeah, no, I write them. Or at least I curate them, let's say, because it's often easiest to just go around. There's so many problems out there. You just find problems and adapt them for your purposes. But could be on the exam. So let's go back to the slides and talk about another way to solve circuits, okay? So this technique, think of this as something that can be used on the previous circuits. This is not a new thing as much as it is a different approach. Okay, so you can still use the technique I'm about to give you on everything that we just solved. You might find that it's easier, you might find that it's harder, just sort of depending on which circuit that you're solving. Typically though, it allows you to solve more advanced circuits. Find out all the little details. It allows you to solve more advanced circuits, such as this lovely circuit that you see drawn on the right side of the screen. Do you notice anything that's a little bit odd about this compared to ones that we've been doing? There's 2 batteries. So if there's 2 batteries, you might start to look at this and be like, I don't know where the current's going, right? Because it's like, I want it to come out of the positive side of this, and then you might say like, yay, it gets here, and then it splits, and then you'd get over to this one and be like, uh-oh, I've got it going the backwards direction. It's running, and then it's like, I don't know which battery wins, which one is stronger, which way is the current actually going to go. Really, the only way to do it is to mathematically work it out and let the equations tell you what's going to happen, okay? So it turns out on this slide and on the next, there are 2 rules that you have to follow. And then I'm going to tell you all the math that you have to know to how to put this together. Let me warn you in advance, this tends to be confusing for people. So if you'd like, I could talk at 50% speed. Would that help?
Yes.
It would? What about 1.5x speed? I don't know that I can pull that off. I don't know. If you, I don't know. Have you ever like accidentally listened to like a podcast at normal speed that you normally speed up? And it sounds like everyone is talking like this all of a sudden. And it just drives you nuts. People listen to podcasts, right? Why do you speed it up?
No, why do you speed it up?
Why?
That's the weird part.
No, it's everyone speeds up podcasts, right? Yes. Who says yes? Who says no?
I don't trust it.
Who doesn't listen to podcasts? How about audiobooks?
Yes.
Yes, audiobooks, you speed them up, slow them down.
Sometimes.
And sometimes kind of depends on the reader. Yeah, generally I just kind of turn the speed up a little because it's, it's like this thing's like 5 hours long. If I can listen to it in 4 hours, all the better, right? Then I can squeeze more in. You're laughing at me like it's the most ridiculous thing you've ever heard. Huh. It's usually not that much faster. I can handle like 1.3, and after that I'm kind of like, I have to focus too much to catch all these words. But I know some people can do like 2x, and to me that's just like, I don't know what just happened. So, okay, never mind. Forget any of that. I'm going to talk the way I normally talk. If you need to stop me, okay? So, 2 different rules. Kirchhoff's junction rule, and on the next page, Kirchhoff's loop rule. The junction rule is the easy one. Notice, it just says that the sum of currents into a junction, I'll tell you what that is, has to equal the sum of the currents out of the junction. In other words, this is almost common sense, okay? It's just saying that if you have some current and it decides to split, right? It's like some of the river goes this way and some of the river goes that way. The amount in those 2 branches has to equal the amount that went into the split. The amount that goes into the place where it splits has to equal the amount that comes out. It's not like all of a sudden like the river splits and 50% of the water just vanishes. It's like it's all got to be accounted for. All of it is there. Now, when you see this term junction, if you look in the textbook or if you've ever seen any of this before, sometimes this is called a node, just alternate terminology. And literally, a junction or a node is just anywhere in the circuit where there's a breaking point, where there's a split, where there's a fork in the current and it has a choice. Just like the way we've been analyzing parallel circuits, that's what we're talking about, okay? So looking at this circuit on the right, there are only 2 points in the entire circuit where there seems to be some splitting point, where I have 1 wire that turns into 2. No matter which direction you look at it, it's 1 wire turning into 2, okay? So notice, they've labeled a few things for us over here. They're saying that some current called I1 is entering junction A, and it splits 2 different directions. The 2 new currents are I2 and I3, but those 2 have to add together to give me what we started with, okay? So I can write down an equation for this and just say that I1 equals I2 plus I3. Boy, that was hard. Take a deep breath. I know, just, right? Yeah, it was either or one of those, which I don't know which one is. I feel like is newer and back like 10 or 15 years ago it was all about when like I don't really know. But you laughed more about so either that means it's older or that means I can't tell. I have no idea. All right. So either your head's exploded or it went over your head or maybe it just slapped you right in the face. I have no idea what happened. Okay. Either way, it shouldn't be terribly hard. If I work my way around, notice follow I3 down, follow I2 around here. This is where they come back together. Well, this is just the opposite of what happened at the top, right? They're coming back together, which means here I have to have I1 again. They recombine to give me that original current. So that's I1, and you can see it tracks back around and connects to the one at the top. So if I wanted to, I could write an equation for this junction as well, but it's going to look just like that, right? The two junctions are doing the same thing, just in reverse. Question?
So current isn't lost as it crosses the battery?
Current is not lost as it crosses a battery. Potential changes, but current doesn't. Okay? So it works out that you could say for every two junctions in the circuit, you get one unique equation. Because there has to be, if there's a splitting point, they have to come back together eventually. So that pair of junctions will yield the exact same equation. So for every two junctions in a circuit, you're going to get one unique equation. Right? That's Kirchhoff's junction rule. You're okay with that one? I'll take just a moment to give you a chance to take it in before I go to the more difficult one. Yes?
So current could cross the battery?
Current is crossing the battery from our standpoint, yeah. Yeah, it's just flowing right through there. Yeah, sure.
So how does the other battery affect it?
The other battery, you will see on the next slide how the other battery affects things. At this point, we're just looking at the current flow. Yeah.
So would the current out of E1 and E2 be the same?
They're two different parts of the circuit. I wouldn't necessarily say the current out of a battery or out of another battery, but all you can say is that the current along this part of the circuit in which there is E2 is different than the current for this part of the circuit that happens to contain E1. So it's like there's three parts of this river. Each part of it has a different amount of current in it. All right? The effect of these batteries is coming up. At this point, we're just thinking about the current. Every branch in the circuit gets a different label for the current because it may or may not have a different value. Yeah.
So the current starts at E1 because you decided to, or was there something that
We didn't necessarily say it started anywhere.
So current, I have the current start in the middle and just go around on both sides.
You could do that too.
So what? Just,
Not really. The only key point here is that you find the junctions and just say that whatever goes into a junction has to come out of the junction. Okay, if you make it that far, I'll show you how to deal with the different cases like you're talking about, all right? Something that's going to bother you as we're kind of leaving the slide and as we go through the next one is that there's multiple ways to solve these problems. You have to make some assumptions up front and trust yourself. You're thinking, yeah, I see people, it's like, trust myself. I don't know anything about physics. Well, see, that's the beauty of it. As long as you just make the assumptions in the way that I guide you into making them, all of your assumptions will be correct, and then the answers will come out okay in the end. Okay? There's enough versatility in these two rules that it sort of accounts for all the possibilities that you may come up with. Let me just keep going, and then everyone's going to feel a little bit better, all right? The next one is the loop rule. In the loop rule, remember how I sort of described the circuit as being like a loop of water, right? And it's sort of like, well, the battery like makes the potential go up. And then anytime the current flows through a resistor, the voltage or the potential drops, and it flows through another resistor and it drops. And it has to get all the way back around to zero, and then it gets looped up again. And it's basically just this thing of uphill, and it goes downhill. And then the battery takes it uphill, and then it goes downhill, et cetera, et cetera, et cetera, et cetera. Yes, you remember some of that, okay? That is essentially what the loop rule is doing. It is saying that if I add up all of the changes in potential around any closed loop, in other words, I add all the potential increases caused by batteries and the potential decreases caused by resistance, if I add them all up, they have to add to zero, okay? Let me see if I can explain. So let's say I started right here, like as a person, as a human in this building, okay? And I can walk all over this building. Sometimes I can go to different floors. Sometimes I can just take steps to do this, okay? And maybe I'm gonna go around this building and go in a closed loop. By a closed loop, it means that we start in the same place that we finish, okay? In other words, I'm coming back to the starting point again. So let's say maybe I start here, right? And I step down, all of a sudden I've had what we might call a decrease in potential. And let's say I walk over here for a while, and maybe this is like I'm on a wire, like nothing's really happening, no resistors, nothing's happening, I just wander around. And then I go out here, and I wish I could just like keep talking to you as I actually walk around the building, that'd be kind of fantastic. But maybe I go down the hall, and I find a stairwell, and I go down the floor. Another potential drop. And then I go all the way to the other end of the building, and I find the stairs, and then maybe I go up 2 floors. Maybe that's like battery, right? And then I go all the way down the hall again, and then I come back down. What floor are we on now? I've lost track. I'm 2 floors above or 1 floor above? Okay, then we come back down to this floor, and I've got another potential drop. And then I walk back into this classroom and come back and step up this step and come to right here in this exact same place again. That's a closed loop. I finished in the same place that I started. And if I finish in the same place that I start, I know it might blow your mind again, but I should be in the same place, right? That was almost, the fact that I said it almost made it make no sense, right? If I'm back in the same place that I started, I have to be in the same place. Meaning I can't now be a floor above or a floor below. I have to be right here at this level. Otherwise, I'm not in the same place. I'm somewhere else. Agreed? Okay? So as long as I make a closed loop and I finish in the same place, I end up in the same place. Meaning, if I add up all of those ups and downs that I described, I went down, I went up the floor, then I got some positives, some negatives, some positives, and negatives. If I add up all of those ups and downs, the total has to be 0. And I had no net up or down. If there is a net up or down, then I'm not back in the same spot. Yeah.
So could this be synonymous with work?
Synonymous with work. How so? Tell me more.
If you apply a force in every direction, you will only end up back at x1. You essentially created a network.
Yes. If you're thinking about work and the fact that work involves displacement, it's the same idea. It's basically the idea that there is no net work done as long as you traverse around the closed path if it's a conservative force. That's physics 220. But yes, same idea. Okay? This is what's happening in the circuit. We're going to go around part of the circuit in a closed loop and end up right back where we started. And as I go around the circuit, there's going to be times where my voltage goes up because I've crossed a battery. Sometimes it goes down. Sometimes it goes up, down, a bunch of different amounts. When I get back to the same place, I have to be at the same level of voltage that I started at, which means there can't be any change overall. Okay? So that is what Kirchhoff's loop rule says. The sum of changes in potential around a closed loop has to equal 0. So they've sort of illustrated it here with a circuit that doesn't have any parallel stuff. It's just literally one closed loop. And they're showing you, as you go to the different points in the circuit, what happens with the potential. And I think, it doesn't quite line up, but you get the point, okay? So notice, point D corresponds to this point that's right next to the low side of the battery, the negative side. So there we say the potential is 0. As we work our way from D over to E, notice I'm going from negative to positive. I'm going from low to high. That is a step up in potential. It's like going upstairs. So you can see from there to there, we go up 12 volts. Then, as I go over to point A, nothing happens. There's no resistor, there's no battery, there's no anything. It's just staying right at that level, right? When I then follow the current through that resistor, it's like the current is flowing, it gets to the resistor, and it's like, and it goes downstream to the other side of the resistor. And you can see that reflected as we go from A to B, the voltage drops. So this point B is in between the two resistors. I've lost part of the voltage, okay? Started at 12, now we've dropped down to some intermediate value. After I go across the other resistor, it drops the rest of the way, and then we're back to the starting point. We're back at 0. So I had some ups and I had some downs, but when I add them all together, the change is 0, okay? Yes, you're alive? Yeah, okay. So let me show you how to apply this mathematically. It just turned off. Don't turn off. Why would you do that? So here's what we're going to do. Let's see. When it comes to the loop rule, we are going to say a couple of different things. First of all, for resistors. For resistors, a couple of things are true. We're going to put in the circuit a negative IR. Remember, that's basically voltage according to Ohm's law. Negative IR, a step down in voltage if analyzing in the same direction as the current. It's a step down if I'm analyzing the resistor in the same direction as the current. In other words, if I'm sort of looking at the circuit and pretending I'm flowing with the circuit. So I think the best way to describe this is maybe you are just outside of the river of current and you're like watching what's happening. You're on the river bank now. And so maybe you've decided to walk around the loop in the same direction that the current's flowing and see what happens. When you get to a resistor, you're going to see that the current goes down, as does like the side bank of the river too, which means we have to put into the equation a negative IR. But it's possible to like analyze the circuit by like walking alongside the river in the opposite direction, right? The current could be flowing this way, and I might decide to walk along the side of the river of current in the other direction and just look at what happens. Well, if I did that, I would be sort of like walking upstream, in which case I would put into the equation a positive IR if analyzing in the opposite direction as the current. And you are going to be doing it both ways sometimes, just depending on how the particular circuit sets up, okay? So if I'm analyzing the circuit in the same direction the current's flowing, we treat a resistor as a voltage drop. If I'm analyzing the circuit upstream, we treat that as a voltage step up, okay? If you go back and look at this particular diagram, it's just the difference between sort of tracing through the circuit this way, which is the direction the current's flowing, and tracing through that way. If I look at it in this direction, which is the same way as the current's flowing, then when I get to this resistor, the voltage goes down. When I get to this resistor, the voltage goes down again. If for whatever reason I decide to like look at things from this direction, when I get to this resistor, the voltage steps up. And when I get to this resistor, the voltage steps up again. So your analysis direction is just which order you're sort of looking through the items in the circuit, okay? When it comes to voltage, so we'll say for batteries, the current direction doesn't matter. All we're going to say is that you put in a plus V if analyzing from the negative side to the positive side, and a negative V if analyzing from the positive side to the negative side. Positive V or negative V. That's just about whether I'm looking at this battery going this direction or I'm looking at it going the opposite direction. In one way it's a plus, in the other way it's a negative. Those are the rules that we're going to use, but I'm going to give you like a series of steps to follow that hopefully will lead you to some answers if you sort of go through each of these every time. And let me quickly look and see which slides I have here. Okay, good. So here's just a sample circuit. Just a sample circuit to show you something about, say, choosing analysis loops. Choosing analysis loops. These loops have to be closed, and it really doesn't matter as long as you start and end in the same place. So just looking at that circuit at the top, there's many different things that I can do and have a closed analysis loop. And you can literally pretend like you're just sort of walking around the circuit. So I could do something like, okay, great. Maybe I decide to start here and look at everything in the circuit working my way around this loop like so. Yes, that's just part of the entire circuit, but it is one complete closed loop where I end up in the same place. You can see that reflected here below, okay? It's going around the left part of the circuit in a closed loop in a clockwise direction. I could also say, okay, I want to analyze a different part of the circuit, and maybe I decide to start right here and go and analyze this part of the circuit in that direction. Well, that's reflected in this diagram here below. It's a different closed loop that's in the same circuit. Notice there's another option, and this isn't all of them. I could just say, like, okay, I'm going to start at this same point, but this time just analyze the entire outer part of the circuit and come back to where I started. And you can see that that's reflected in the diagram on the bottom right. Those aren't the only closed loops. They're sort of the three, I guess, shortest closed loops. But if I wanted to, if I really wanted to get kind of ridiculous, which I don't think any of us want to be this ridiculous, you could do something like start here and be like, ooh, I'm going to go over here, and then over here, and 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 then around like a couple more times, and then maybe back to where I started. That would be kind of the equivalent of the way I describe myself walking around the building. All sorts of different directions, like I'm just going down the different hallways of the circuit, and I just come back to where I started. Perfectly valid. It's overkill though. You really don't need to do anything like that. I could just start here and like make a figure 8. That would be perfectly valid too, as long as I just end up where I started, all right? I'm gonna delete those last two because they are kind of pointless, okay? So let's work through the steps that you have to follow. I'm gonna do a problem for you, then you're gonna do one, and then we're gonna go home, and that's gonna be the week, okay? So here are the rules. Number 1, you are gonna look at each branch of the circuit and give the current in each branch a name. I1, I2, I3, I4, I5, doesn't matter what you name them, okay? Just look for every unique branch of the circuit. And you are just going to assume a direction for each of those currents. You might be correct, you might not be. The equations will fix it for you if you're incorrect. So all you need to do is look at the circuit, find every unique branch, give the circuit a name, and just say, I'm just going to say this direction is the direction the current's flowing, okay? So let's actually do each step with a practice circuit. So I'm going to draw a circuit on the next page, and And we're gonna do step 1 before I describe step 2. So sadly, I didn't put the circuit in here, so we all get to have a little fun drawing a circuit. Oh, let's see. It looks something like this. There's a resistor here, and then it comes back around here and goes there where there's a battery, and then there's a resistor, and then there's another resistor, and let's see, down here is a battery, and then another resistor, and then one more resistor. I'll let you draw that, and then I'll put some numbers in. You'll notice there are 2 batteries. I'm going to say this one is 45 volts, and this one down here is 80 volts. And then resistors starting from the top. We'll call this one a 30 ohm resistor. This one is a 40. This one is 1. This one is 1. And this one is 20. And I think that's everything. You'll notice we have a value for everything except the current. We don't know the current anywhere, but we have values for all the resistors and both batteries. We could flip a similar problem around where maybe I give you the currents, but I leave some of these blank. You'll find that there's always just going to be a few unknowns, and you'll use the same approach to find them because you're just going to end up with some equations and some unknowns, and you're just going to solve them, okay? Does everyone have the circuit down there before we talk about loops? Or excuse me, currents was the first thing. Everybody's good? Okay. So looking at the circuit, there are 3 distinct branches. And you can get that by just looking at one of these junctions and see that there's a wire coming in, and then it has 2 places it can go. So it makes sense that there's 3 different branches for the current. So we're just going to pick some. So I'm going to go to a different color and say that the current that's going around this way, around the top part, is called current 1. I just picked that direction. If you want to go the other direction, it does not matter at all. We're labeling it, giving it a name, and assuming a direction. I'm going to say that the current that goes around the bottom side, like so, is current 2. And I'm going to say there is one last current that goes right down the middle. That is current 3. Directions are made up. We did step 1. Congratulations. Step 1 was pretty easy, right? No math. You're just like, hey, I'm going to draw arrows and assign names, and I'm correct. All of you are correct on this point. You can't get this part wrong. Right, Gabe? You said, yeah, you can? Yay? Oh, yay. Okay. Yeah. You can't get this wrong. Yay. Yeah, it makes sense. So let's go back to step 2. There we go. We did 1. Go us. Is anybody going to get candy immediately after this? No? Question back there?
So, can you go back to the picture? Oh, cool. The top left is which current?
The top left,
Red line.
that's all I1. Everything that's going around the top is I1. Everything that goes through the middle is I3, and the whole thing around the bottom is I2. Other questions? Yeah?
We don't necessarily have to have this orientation, right?
Nope. You can make them all the exact opposite direction, doesn't matter. You can flip half of them, doesn't matter.
You can have a different, so like you have I1 coming out of the volt, and then
Yep.
it's splitting off of I3.
Yep. The names don't matter, the directions don't matter. The only thing that matters is that you have 3 currents. There needs to be 3 different currents in the diagram. So let's do step 2. Step 2 says, apply the junction rule to each junction that yields a different equation. Remember, for every 2 junctions, we're gonna get 1 unique equation. If I go back and look at my circuit, well, I have 2 junctions. So if I can look at either one of them, they're going to give me the exact same equation. Notice that I3 is labeled as going into this junction and splitting into I1 and I2. So I'm just going to continue with what I've made assumptions to be. So applying the junction rule, we can say that I3 equals I1 plus I2. We have 1 equation and 3 unknowns so far. So alas, algebraically, I can't do anything. We need 2 more equations that includes those same 3 unknowns in order to algebraically get a solution. That was step 2. Step 1 and 2, not that bad. Make some assumptions, apply the junction rule once for every 2 junctions that you have, okay? Now, you can see I've also written here the rules that we put on the previous slide. We're going to apply the loop rule for as many loops as we want to. The thing is, every time I do this, I'm going to get 1 equation. I just need 2 more equations. I'm still probably going to do it 3 times just to give us some practice, okay? So applying the loop rule means going to this circuit and just picking closed loops for analysis. The only thing you need to do is be consistent with your direction, okay? So if you decide that you're gonna analyze things in a counterclockwise direction, just do that for all your loops, okay? So what I'm going to do is say that my first analysis direction is going to, say, start in the top right corner, and I'm gonna go around the circuit this way. And go back to where I started, and I'm going to call that loop 1. Yes, this diagram gets messy. I'm trying to help with the different colors and trying to be somewhat neat, or so maybe the normal, I don't know. So we're going to look at that as our first loop. And we're going to write an equation following the rules, okay? So literally pretend that you are starting on the circuit at this point, and we're just going to go, there's a thing, and then there's another thing, and then there's another thing, and then a thing, and then we're back where we started, okay? Every time we hit a thing, I have to put something in the equation, okay? So let's start here again. Notice I hit the negative side of the battery, and I'm working my way this direction, so the next thing will be the positive side of the battery. You can consider this to be a step up in voltage. I'm going from low to high, okay? When I say I'm going, that is literally just which way I'm deciding to sort of analyze around the circuit, okay? So as I go from here across this, I'm gonna put into my equation a positive 45 volts. That's what happened as I crossed that battery. And again, we are applying the loop rule. And specifically, this is for loop number 1 in the circuit. You will notice as I continue to do this, look, I'm flowing right with current I3 as I go down this middle branch. As I go down the middle branch, I3 is assumed to be going the same direction. So as I get to this next resistor, and I analyze across this resistor, I'm analyzing it in the same direction that the current's flowing. According to our rules, if I'm analyzing in a direction with the current, that is a negative current times resistance, according to Ohm's law. So we will write in our analysis, well, the current is I3, and the resistance is 1. So I'm going to write that as negative 1 times I3. I just flipped them around because the coefficient should really be out front. Otherwise it gets a little weird if I write I3 1. That doesn't look right, okay? What do you think I'm gonna write next? Yeah, when we get to the next thing, I'm still going in the same direction as I3. So this is a step down in potential, which can be written as negative 40 I3. Okay? Does everyone so far understand the three things that I wrote there for those three circuit elements right down the middle branch? We have a step up in voltage, followed by a drop and another drop. Okay? Let's continue around the circuit. Everyone sing along. I went off the screen. We found the 30 ohm resistor. Notice, now I'm analyzing this in the same direction that current I1 is flowing. Okay? So we're going to write in our circuit equation minus 30 times I1. And then the next thing that happens is I'm back to where I started. When I get back to where I started, I'm saying that adding all of those up results in no change in potential. All of the ups and all of the downs should equal 0. Can I combine a couple of things and just sort of simplify this real quick? So I've got 45 minus 41 I3 minus 30 I1 equals 0. So loop 1 yielded that equation, just combining like terms. That 3 is terrible, isn't it? Wow. 3. So now I've got 2 equations and still 3 unknowns. I need one more equation to solve a system of equations. So let's do another loop. We're just going to pick another closed loop. I'm going to go around this bottom rectangle. I'm going to, again, start in the top right. It kind of helps me. I don't know if I have some consistency. You don't have to start in the top right. You don't have to go clockwise. It's fine if you want to start in the bottom left and go counterclockwise. It doesn't really matter. Just pick something and be consistent. So let's see. I'm going to start here. We're going to call going around like this loop number 2. Okay, so here we go. We're just going around the circuit this direction, going around that direction. So starting at this corner, the first thing that I come to is this 20 ohm resistor, but you'll see that I'm going opposite to the direction of the current. It's like I'm going upstream. I'm starting at a place where there's a lower voltage, and I'm going to a place where there's a higher voltage. In other words, if I'm going to write something in the equation for that first resistor, it's going to be plus 20 times the current that's passing through it, which is labeled as I2. It's a step up in potential equal to I times R when you're going against the current flow. And we're going to be going against the current flow when we get to this next one as well. Okay? So now I have a 1 ohm resistor. Current I2 is flowing in the opposite direction. So the next thing we're going to write is plus 1 times I2. And then what am I going to write next? Looks a whole lot like we're going to go from the positive side of the battery to the negative, and it's worth 80. We're stepping down 80 volts. And then we've got all that stuff in the middle. So let's see, coming around this way, the next thing that I run into is this 40 ohm resistor, but notice we're going to go the opposite direction this time across all of these. So we're going to have a step up, another step up, and then a step down. So I'm going to quickly write those down. Bear with me as I start to accelerate through the problem just a little bit. So across the middle, now we're going to have plus 40 I3 plus 1 I3 minus 45, and then I'm back where I started. I times R for each of the resistors, and then just a voltage, positive or negative, for the batteries. So you'll notice we have 2 I2 terms, 2 I3 terms, and 2 just numbers. Let's combine some like terms just to make this neater. So we've got 21 I2, and it looks like 41 I3 minus 125 equals 0. we applied the loop rule twice. At that point, that's all you need. You've got 3 equations, 3 unknowns. There are a number of ways at this point in your life where you should know how to solve systems of linear equations. If it scares you, maybe look it up over the weekend. I don't really care if you do it completely manually, where you basically either use substitution or elimination. There's some words from your past probably, okay? And put all those equations together and mash them together until you're able to solve stuff. Or if you just know how on your calculator to like input a matrix and just hit solve and it gives you the answers, that's totally fine as well. I don't care, okay? Essentially, here what we have is 3 equations, 3 unknowns. This is a linear system of equations. If you stop right there, we've applied the loop rule as many times as we need to get the number of equations we need for the number of unknowns, which means you solve the equations for the unknowns, and I will tell you what those values are so you can compare to whatever results you come up with over the weekend. So you should get, where are these answers? I1, well, let's do the other direction. I3 is 1.75 amps. I2 is 2.6 amps. And interestingly, I1 is negative 0.85 amps. All that means is that what we assumed for the direction of current I1 was backwards. That current I1 is actually flowing around the top the other direction, okay? So that the equations and what we get for signs tells us something about the actual directions of the current, which means if you had picked different directions and analyzed different directions, you'd get the same numbers, but maybe some of the signs would be different, and then we'd all end up in the same place for what the actual direction is. And there's something that's just kind of cool about that. That there's all this freedom that you can kind of like, solve it your own way, and then we all end up at the exact same result. I would challenge you to try this over the weekend. Make sure that you know how to take those 3 equations and get those 3 answers, okay? Questions, thoughts, comments, confusion? Maybe? Waiting. And I'm gonna let you go there. We don't quite have enough time for you to solve a problem on your own. And that was heavy. I felt the weight on your shoulders. So go buy candy and bring me data on Tuesday. Yes, data about discount amount and how many days it's been since Halloween. And then we'll know something. We'll learn something really important. Goodbye. Have a good weekend. Have fun. Do your homework and other things. Bye. Goodbye. Farewell. Goodbye. You're welcome. Bye-bye.